Hello and good evening, everyone. I am Ravleen Bajaj, and today, on the behalf of Google Developers Club, Shahid Rajguru College of Applied Sciences for Women, I welcome you all to this session for Data Science 101. And I sincerely hope that you will have takeaways from today's session, and it will be an interactive evening for all of us. So, I'll be presenting my screen, and I hope that all of you will be able to see what. Okay, so I hope my screen is visible to each one of you. If somebody could confirm, that would be great.
Yes, Ravleen, it's visible.
So this is how a Jupyter notebook looks like, and we will be operating on a real data set, which is the iris data set. It is given by UCLA, which is University of California, and you can find it, or you can easily download it on Google. Just search for iris dataset and you'll find a CSV file, a very small CSV file, 5 KB maybe, and you can download the dataset very easily. So that is how we got the dataset. After we get our dataset, we just have to load it in Jupyter, and then we can start our notebook. So this is a prerequisite, that you need to load your data set in Jupyter, and then you can read it later, as we will be doing here. So I'll be starting now. So this is how the interface of the notebook looks like, and this is the name of the notebook. You can name it to any name. So right now it's DS101 because this is the name of our session, and that is how I wanted to keep it. You can save it at any point. You can cut cells. So if I click on this cell and I press the cut option, this cell will be removed entirely, although we do not want that to happen because all of our libraries are being imported from here. So that is, there are other options as well. So these are the options for the kind of cell we want. So if I change it into heading, so this will just be a textual cell, and I'll be able to add only text. It will be interpreted as text and not as code. However, this is a piece of code, so we do not want that to happen again. So we will keep it as code only. So today we will be doing basic descriptive statistics, which is mean, median, mode, coefficient of variance, very simple descriptive statistics. After we are done doing that, or before that, we'll obviously learn how to import these libraries and how to uh, convert our data set into something more viewable and desirable, and something that is more easy to work on while we are doing certain data science analysis or techniques. So post which we will be post descriptive statistics, we will move to a little higher level of statistics, which is the t-test, and it is basically used to check a hypothesis. So we pose an assumption, and the t-test will help us see if the assumption is right or wrong. So that is how we'll be proceeding in the session today. And while we're doing the t-test, we will be doing visualizations through Seaborn, which is again a library in Python. You can simply import it, and that is the flow of today's session. So let us begin. So the first cell has all the libraries that we'll be needing. So we'll be needing pandas, we'll be needing NumPy, we'll be needing Seaborn, which is for visualization. NumPy is for all the calculations we'll be doing. Matplotlib is again for the mathematical operations and plottings. Random is to generate a random variable, and SciPy and stats models are for all the statistical tests that we'll be conducting. So we won't be getting into the details of what actually the t-test is, we will be more focused on the results and how we can draw inferences from the result, because that's precisely what a data scientist does. And if you want to get into the mathematical aspects, you can simply get the formulae from the internet, which is very easily available. So this is the first cell and I'll just run it. So since there's nothing that needs to be printed, so it just simply goes to the next cell. Now we'll be reading the iris CSV. So this is this name of the CSV that is saved on my system, and df.iloc is basically used to access the values in a table. So the first zero colon, the value before comma is used to access the x is used to access the rows, and the next one is used to access the columns. So since since the 0th index column was simply the uh, numbering or the serial number of the data set, and we do not need it and it's not relevant for our analysis, so I simply ignored it and chose to import the data set from the second column of the data set, and then I renamed the columns to something which is more readable and desirable. So these were this is the original name of, say, the sepal length. So this data set is basically about species of flowers with different sepal lengths, widths, petal lengths, and widths. So I'll be showing you the data set in just a bit, so don't worry, so that you will be having a better understanding. But this particular line of code just enables you to have a more meaningful name and a more visual name to your data, give so that it's more interpretable by the user. Then this command is used to access, so the LOC command here is used to access the sepal width of a given species. So versicolor is the species that we are particularly accessing over here, and we want to access only the sepal width. So I've put the print command in the hash so that we can actually see it right now for ourselves. And if I print it, so this is the index value of the of each value of sepal width from where the versicolor sepal width values start, and these are the values of the sepal width that are there. So if you see, this is the head of the data set, and sepal widths are 3.5, 3, 3.2, 3.1, and so on. So when I print values from the fifth index in the data set, so you can see that it is versicolor, which indicates that the command that we run previously was correct. And I'll put this in hash because it's very long. So similarly, we also accessed values for Virginica and Setosa, so that we can, so basically we are accessing sepal widths for different species of flowers. And now this is how the data set looks like. This is how the data set looks like in the CSV. These are just the first five values in the data set. However, the data set originally has 150 values. So since we do not require to see all the values to understand what the data set looks like, we've just printed the first 5 values. So if anybody has any doubts for now, feel free to ask, otherwise I'll proceed. Okay, so I'll take it as a no for doubts and we will be proceeding. So now we will be moving to basic. So this is how you index values from your data set. So from the 5th index to the 149th index, all the values are here, and we have 3 dots because Jupyter does not print all the values, and however it is shown that 100 rows are there. So I could just maybe index, say, 10 values from this. So it'll be like this, and if I run it, so only the first 10 rows will appear, and these are all for the Setosa species. So there are 4 or 5 species in this data set, and we will be working on those species, working on different, we will be segregating data on the basis of species only while we move ahead. So now we'll be doing some basic, extremely basic descriptive statistics. So we know that mean is the average of the population. So average of population is mean, and when we will be calculating the mean for the sepal length only. So all the sepal lengths 150 values, the mean will be 5.843. So we could also easily calculate mean of, say, sepal width or petal length or any other or petal width for this data set. For any given column, we could just calculate the mean, median, mode, anything. So the mean for sepal width would be 3.054. And similarly, we could calculate the median or the mode. And for standard deviation, we will be using the std command. So all these functions are taken from the NumPy library, and that is possible because we imported NumPy initially in the first cell. So now we will be seeing standard deviation, and we can also calculate variance. So however, we do not have a direct command for coefficient of variance, and for that the formula of coefficient of variance is standard deviation upon mean. Again, a very basic formula and a very basic statistical measure to evaluate our data, and simply we will be calculating it by SD upon mean and printing it. So now we have our variance, our standard deviation, our mean, median, mode. We can also calculate range, central tendencies, interquartile range, and other basic descriptive methods, evaluations, to just see how our data appears to be. And if you have any doubts, so feel free to ask, because after this command we are going to go full-fledged data science 101 from post this command. Okay, so I believe that there are no doubts for now. And so this is how we set the theme of our figures. So we will be printing graphs for the t-tests. So 1 sample and 2 sample t-tests, we'll be doing both of them here. And this is how Seaborn enables us to give a theme for all our plots. And the RC is basically runtime configuration, and this we have basically mentioned it in our brackets because we do not want Seaborn to use its default default visualization appealings, and we want Seaborn to use our theme instead of its own default theme. So this is how we will be using the colors. So this is line width, so the width of our lines. So if we see, this is the grid that will be coming, and these very tiny white lines are the line widths. So the line width is very less, and that is good because we do not want these lines to actually come over our actual figures. Then we have the grid color, which is white. So our grid is white. You can already see the lines are white in color. Then the axis line width is 2, and axis space color has a color code, which is basically the color code for the axis, and the line width is 2 again. Label color, again the color code, so the label is black, I guess, and so is its color code. Then the X-tick color and the Y-tick color are the color for the values. So say 2, 2.53, 0, 0.2, all these our X tick and Y tick values. So the colors are again mentioned as in the color codes. And this is my palette one is this is just for your reference. We will not be using this palette in our code here, and it is basically the colors that we will be using for. So these are the colors that the sea green theme that I've picked. These are the color codes for those colors, and red color just for instance. So this is basically a list of the colors that I want to use in my palette or in my visualizations throughout this particular session. So my palette one has 3 colors. I could add more. I could say I could add blue maybe. And then when I use this palette in my visualizations while I'm actually running commands, so it will simply use blue color also wherever it's required and necessary. However, I do not need any of these colors. I'll be using my palette 2, which is basically the blue colors for visualization. That I just particularly like that theme. You can use any color for your reference. Okay, so I see. Are there any imports for the program? Yes, so I already pre-downloaded the iris dataset in this file, in this Jupyter node, in my Jupyter kernel, and you can also pre-upload files, all the files that you want to. So you go to the kernel, and if I go to the kernel, I might lose my progress, so I won't be doing that, but I'll show it to you in the end. So you go to the kernel and you just, there's an upload button. You just click on the upload button and you select the files from your device, whichever file you want to upload on the kernel, and you simply upload it. So that way you can upload the files to the kernel, and once you've uploaded files, then you just have to read them through this particular command which I used, the first command in action. So pd.read_csv. So I read it through pandas. You can also read it through other ways. Then we come to one sample t-test. So although I won't be getting into the numerical parts of this, but I'll still explain what a t-test is and what inference you can draw from it, so that whenever you use a t-test, you know how it goes. So a t-test here, one sample t-test is usually used to know if the population mean is equal or not equal to a sample mean. So population mean, by population mean I mean the mean of all the values in a given data. So here we had 150 instances of 150 rows or 150 values. So the mean of the population was for different columns was different, and that was the population mean of a given column. However, sample mean is selecting random 5 or 10 values out of this data set, or even more, or any number of values, and calculating the mean. So we essentially compare them and see if they will come out to be equal or not. So that is the purpose of a t-test. I hope nobody has any doubts. Yeah, okay. The requirements are that the sample should follow a normal distribution. So this particular sample does follow a normal distribution, and this has already been worked upon a lot by people at UCLA and different other individuals. This data set in particular, you'll find all sorts of calculations on it while you try to Google it, and that is primarily why I chose this data set, so that you can actually look through other processes and visualizations if you feel more curious to learn about this topic or this data set in general. So this data set, as you can see, this is a approximately normal curve, and so our prerequisite condition is followed. However, we do not know the sigma square here, and sigma square is basically the variance, and we do not know the sample variance, not the population variance. We know that, and our decision will be based upon a hypothesis. So H0 is known as null hypothesis, and null, it's basically the primary assumption that we are taking, nothing else. It's just a fancy term to call it. And p value is the probability value, say 3.5. So the p-value could be 0.05 over here, which means that post 3.5, so this space in the graph covers only 5% or 5 upon 100 probability of our data contains. So which means that if p-value is less than 0.05, we will be 95% confidence, or we will be 95% confident of our analysis. So which is a great number, to be honest, and that means that we could accept our hypothesis. However, if the p-value is less than alpha, alpha is basically a threshold value which we set for ourselves. So it's basically a constant. So for example, I said 0.05, it could be 0.1, 0.2, 0.5, any number. So if the p-value is less than the alpha, then we reject the hypothesis, because then we cannot be confident of our data. However, if it is more than the given value of alpha that which we have chosen for our data set or our data, then we can pass the hypothesis, and our test is said to be successful, or we can draw inferences accordingly on the data. So now I think we're done with the theoretical part, and just to give you a brief understanding of how to type this kind of text on your Jupyter notebook, I'll just click over here, and you will see these different hashes in the cell, which basically implies headings. So one hash means the largest heading size, and as I keep on increasing the number of hashes, my heading size keeps on decreasing. The maximum number of hashes is 6. It's similar to HTML. However, I wanted this to be big, so I'll keep it at 2. But these are purpose, requirements, decisions. All these points I wanted in a smaller size, so that's how I'll keep them. And when I run it, so it will look cute text like this. Now I will just line by line explain you the code for a one sample t-test, and then I'll explain the inferences that we draw over here. Okay. So df_1 and df_2 are basically what I have done is divided the data frame, not divided, basically taken 2 data frames out of our original data frame, because while we, as a data scientist, it's important that you do not tamper with the original data set. Instead, you just use or index those parts that are relevant to you. You filter content out of those parts. But a good data scientist or a good statistician, even by the matter of fact, does not tamper with the data at all. It's not a good practice at all in research. So we do not do that at all. So here LOC is again used to index the species column from the data set, and the 2 different basically what I've done is I have indexed 2 different species and their sepal width and species name, and converted into 2 different data sets. So now my first df1 will basically contain the iris virginica and sepal width corresponding to each value of iris virginica, and df2 will contain iris versicolor and the sepal width corresponding to each value. So now this command is used. This is basically giving context for our visualizations or graphs here in this case, and DPI is basically the resolution. So dots per index is the full form, and so 150 is the DPI or the resolution that we want. Label size, for the size of the label we want is 9. Again, xtick values, legend, title, font, all of these things are very basic and self-explanatory, so I won't waste a lot of time on them, and what I've done is just set a basic size for them. So now this is an important command, because this converts my my screen space, my plot space into 2 parts, or into a into a 2 by 2 grid. So not a 2 by 2 grid, into a 1 by 2 grid. So one row and two columns, and we could do it into n number of sizes. So we could do it into 3 by 3, 4 by 3, any size. It's actually 2 by 2 because two graphs and two rows. So we are actually converting it into two, converting the screen, dividing the screen into two halves. But we could also do multiple rows and multiple columns. So we could essentially convert it into 3 rows and 2 columns. So we will have 3 rows of graphs with 2 columns of graphs. So this is usually used while we are visualizing scatter plots, these kind of grids. But since we just have 2 plots to view over here, we will be using it, converting it into 2 by 2 grid. The figure size will be 10 by 7. So each figure is 10 by 7 in size. And plt.subplots is the command which enables us to divide the screen space into two parts. In our case, and ax_0 is basically the axis. See, if you see the code over here, we are indexing the axis again because 0, 0, is for the first graph and 0, 1 is for the second graph. So I hope there are no doubts yet. Yeah, there are no doubts. So I'll just zoom in a bit for a clearer view for everyone. So yeah, now SNS.kde plot is kernel distribution estimation plot, and it's again a fancy term. It's basically a density plot for continuous data, and that is all what I mean in this long statement in the comment. And this is a density plot for the sepal width, and we are using the first data frame, so which is essentially the data frame for Iris virginica. And so the common norm is true because it follows normal distribution. Fill is equal to true because again I want the normal curve to be filled in with color, and the color again here is mentioned. So alpha is what we are taking is 0.4 in this case. We could take any value of alpha. This is just a random value that I've picked. And the title is Iris virginica for this one, and the title color and font are mentioned. So now we have the first plot ready. Similarly, we get the second plot ready, and we set its title, and that's how. So yeah, and then we converted it into a 2 by 2 grid, and we set its visibility. So I was right, it should have been 2 rows, but the visibility for these the second row has been turned into false because I don't have more graphs to print. So you simply see 2 graphs, and the index 1 row, which is basically the second row, will not be visible. So now this is basically the layout, and I basically show my plots. So when I run this command, these graphs will be visible. Now you can see that both the graphs follow an approximate normal distribution, and these are approximate normal curves. However, the sepal width is a little bit the iris vertical is a little bit tilted towards the right, but it is still considered as a normal distribution. So this one will work for a t-test. So now we will be conducting t-tests on both the graphs. So this line of code is so this is the mean value that we are taking, and this is the t-test. This is the t-test command we are using, which we have imported directly from the SciPy and Stat Models libraries. So this, if we run this command, the t-test will say that the statistical value of alpha, the statistical value is actually minus 0.57, and the p-value is 0.57. So since p-value here is actually greater than alpha, the null hypothesis is not rejected, and which means that we are actually confident, we are 60% confident in our analysis, because we took 0.4 as alpha. So which means that the confidence interval is 60%. if we would take it as 0.04, it would have been 96%, and so on and so forth. So 0.1 is basically 10%. Similarly, and this is the 3 is the mean value or the peak value of the normal curve. So here it is 2.7 and here it is 3, and that is how I took it for the t-test. So two-sided simply means that p-value from both the corners of the normal curve will be considered. And we run this command and we see that here the p-value is 0.12 and statistical value is 1.57. So since 0.12 is less than 1.57, so according to our given condition, we reject the null hypothesis because the statistical value is different from the p-value, which is already stated, and p-values are already predefined, so there's a formula to calculate it. But even while doing it on a pen and paper or in a notebook, you get a table for p-value which is similar to a log table, and you can refer it similarly. So simply we reject the hypothesis in the second command, and in the first command we approve it or pass it. So now we'll be doing a 2-sample t-test with independent or unpaired samples. So now we will check if the population means of both the groups are equal or not. So both of them should follow normal distribution and both the samples should be independent. So if the population mean are equal, so the null hypothesis is not rejected, and p-value, if the p-value is less than alpha, then again the null hypothesis will be rejected. I again changed this cell into markdown and then converted it into different headings to make it more readable and understandable for the viewers. Okay, so Ashutosh Kumar said repeat. What do you want me to repeat exactly? Okay, so I will be proceeding for now, but you can type it and I'll address it towards the end, because this is probably the last thing that we will be discussing, and then we'll be talking about inferences that we make from a 2-sample t-test. So again, we will be making a third data frame where we'll be accessing only iris virginica and iris versicolor. So again, we set a prerequisite for our plots, which is the DPI, label size, label extic size, legend size, and title font size. Then again, we divide our screen space into a 2x2 grid, where we will obviously be setting the visibility to false for the second row, and we will be making a density plot for the 2-sample t-test that we will be conducting. And a strip plot is basically a scatter plot. It's nothing but a scatter plot, but dividing it into categories. So you can see that we are using the second palette that we created earlier, and this again follows normal distribution. Here again we've taken alpha as 0.4, and the strip plot has sepal width for both the data frames, for both the species, which is versicolor and virginica, and this is how. So we set the visibility to false for the second row, and that's how we show the graph. So we can clearly see that the means are not exactly equal in the t-test of both the graphs, but they're very close. So this null hypothesis will not be rejected essentially in general cases. To be exact, a null hypothesis must be rejected always, but we always keep the confidence limit to 95 or 99% or less. Mostly it's 90 or 95 and sometimes 80. So this would probably come under 95, and so it will not be rejected. This is the scatter plot, and we've created space between the two, so that is how this is how this is why the jitter uh, the jitter function is used. And iris virginica and iris versicolor have sepal widths in these given ranges. So this particular graph enables us to understand what is the minimum and the maximum range of sepal widths for each of the species that we have over here, and how evenly or sparsely or densely distributed the species are, their values are. Again, so coming back to the first graph, the species iris versicolor and virginica are almost have an almost equal population mean, and with a confidence of 95%, we can say that we pass the null hypothesis and we do not reject it. So this is how we conduct a two sample t-test, and that is how you do basic visualizations using Python. In Jupyter, you can use other platforms as well. There's Colab, where you can contribute to codes with your friends. You can use VS Code for yourself. However, you cannot do visualizations over there, but you can still use it. It's great for debugging. And that is it for the learning part. Now I would like to address doubts if there are any. Okay, so Ashutosh says the graph on which basics of data. So I am not sure which graph you're talking about. Please just confirm once. I guess you are talking about these lines of codes. Pad is basically for the difference, the spacing of the graphs. So 1.5 is the spacing between the two graphs. So if I forgot to mention that, that's that. And if you are talking about this algorithm or this line of code, then I'll just explain it. So this is the axis for the graph that we want, at which we want the graph to be plotted. Then the x coordinate or the x axis of the graph that we will be printing is sepal width, as you can see, and the y coordinate is the density. So the density, this is by default in a density plot, because what else will you plot in a density plot? And common norm is equal to true is a condition, because for this plot, because this plot does follow normal distribution, so Python will automatically align the density scale according to a normal distribution, and both the scale axis scale, but the density scale is the one which will be a little more changed than the x-axis. The fill here is true because I wanted the graphs to be filled in. If I don't use fill is equal to true, it'll be just a simple normal line, normal curve, and no color, no blue color to fill in it. Alpha is the value, which random value against which we are testing the one sample t-test, and this is the color code for the graph. Line width is the width of this line, iris virginica, the width of this normal curve that we want to be printed. So I guess I have explained it, and if you are still not clear, please do let me know. I hope it is clear to you. Now I will just take a quick minute to stop sharing my screen, and I will hopefully be able to show you the original CSV file of this data set so that you can interpret the data better. Just give me a second, please. Okay, so I will be sharing my entire screen because that's the only way that I can show you the CSV file. And yeah, so this is it. I hope you can see the CSV file on your computer screens. Yeah, I am sure it's visible. So this is how the CSV file originally looks like, and these were the original column names that were defined by the researchers at UCLA. And just to make the column names a little more readable, we changed them while we were analyzing our data. And so while we were printing the head or indexing different values, the column names were different. We did not use the first column because it was simply the serial number. So that is why I did not, we just have 5 columns and not 6, unlike the original data set. So we can, probably use 3 columns if we want, probably analyzing only the sepal width and length and the species, or probably just 2 or 4, and then it's completely a relative and dependent case, and it's entirely upon you to decide what parts of data you want to access. But whatever you do, you must always ensure that you do not tamper with the original data and you access or reference or index it somehow. And by the grace of Python, we can do that very easily. So that's a great thing. And these are the different species. So Virginica, versicolor, Setosa, and yeah, these are the 3 different species that we have in our data set. And clearly the data set has 150 values. The first row was for the columns. So yeah, 150 values. That is it about the data. I hope there is no discrepancy in understanding the data, because it is essentially very, very important to know how the data looks like before conducting any kind of tests or any kind of analysis on the given data. So I'll stop sharing for a while and come back to the original Jupyter screen. Okay, so I hope this is clear now. And now I will share my screen again and I'll show you the Jupyter kernel. So yeah, I hope the screen is visible again. And now I'll show you the kernel. So I go to Jupyter, and this is how the home page looks like when you essentially open Jupyter. These are the different files that I've imported, and these are the different Python notebooks that I have. So say this is a sentiment analysis that I did with my college professor. These are several assignments, my practical exams, and other data cleaning, computer codes, or other stuff that I have been working on. And to upload or to import a new file or new data set that you want to work upon, you simply click on the upload button. And this is the iris data set that I have here available. So I just click on it and I tap open, and then I click on the upload button. So it's already there. So it's asking me if I want to overwrite it. So since there's no change, so I'll just say overwrite, but it's essentially not necessary. I could have uploaded a different file altogether, or something else that I wanted to work upon, or something else that I wanted to analyze. So that is it for the Jupyter basics. And now this is DS101, the Jupyter notebook that we have been working on. So I'll click on it, and again the notebook that we were working on will reappear. So please spare my internet, it's a little slow. So you can see that my progress here has not gone away at all, and in fact my outputs are intact too, because I did save it timely. So you can also save it timely. You can create checkpoints. So this is a checkpoint that it was few seconds ago, so you can basically do that. Then you can just simply save and checkpoint whenever you want to, or you can click on it. There were 2 checkpoints. So my previous save was at 549. So these are different. So if I would have saved it before this point, other previous checkpoints would have been available, and say my edits did not go as planned and I want to go back to my previous methods, so I could just simply revert it. Now you could download it as different types of files. I do not want to download it, so I won't be doing that. Trusting, this is just something simple. You can print the notebook as it is. You can make a copy, you can save, you can rename, or you can just open a new notebook. So this is all about Jupyter and simple basic data science techniques, that be the 101s of data science. There's a lot more to the 101 of data science, but this is just the tip of the iceberg, or the briefest understanding that we could get in this short span of time. And I hope that you did enjoy learning this, because I definitely enjoy doing all these things. So I hope if there are any doubts, I would love to address them at this point. And if there are not, then I'd like to just hear from you if there are any doubts, or just your reviews. Thank you, Prachi. It's great to hear that you felt that it was easy and interesting. I hope I was of some help while you were learning this. So if anybody has any doubts or questions or something that is aside from these set of commands, feel free to ask them. Otherwise, we can wrap up the. Okay, so you want my LinkedIn profile? I will definitely drop it for here in the chat box. Just give me a second. So this is my LinkedIn profile. You can send me a connection request and drop me a text anytime you want, and I'll be happy to address any questions that you might have regarding data science basics, because we're all learners, and I'm hoping that I'll also be an advanced data scientist soon, and we all can learn more together and collaboratively. So if anybody has any questions, feel free to reach out. If not, then we can start wrapping up the session. Thank you so much, everyone. Thank you. Thank you so much.